Hello everyone and welcome to Control Engineering and Control Theory tutorials. In these tutorials we present real and applicable knowledge of control engineering, system identification, machine learning, optimization, etc. In this system identification tutorial we provide an introduction to subspace identification methods and we develop Python codes that can be used to effectively estimate multiple input, multiple output state space models of dynamical systems. This video tutorial is organized as follows. I will thoroughly derive the subspace identification method. Also, I will illustrate the application of the subspace identification method on this example. We will consider a system composed of two masses that are connected by springs. We will develop the model, we will discretize the model, and then we will try to estimate this model by using the subspace identification method. At the same time, I will develop the Python codes. That is, by watching this video tutorial, you will learn two things. You will learn the theory and you will learn how to implement the algorithm in Python. And to be honest, I'm 100% sure that there is no such a video that explains these two very important topics. That is, theory and implementation. However, before I start with explanations, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as more than 300 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot! We start our discussion with an explanation of the class of models that we want to estimate. We consider a linear state space model having this form. Over here, k is the discrete time instant, xk is the system state, n is the state order, uk is the control input, yk is the observed output, wk is the process disturbance, nk is the measurement noise, and a, b, and c are the system matrices. The vectors wk and nk are usually completely unknown or only we know their statistics. Under several technical assumptions on the statistics of wk and nk that for simplicity and brevity of this tutorial I will not explain, with the system 1 we can actually associate another state space model having this form. Over here, ek is r-dimensional vector and k is a matrix. This state space model is often referred to as the Kalman innovation state space model. The vector ek and the matrix k model the effect of the process disturbance and the measurement noise on the system dynamics and the system output. The system identification problem can now be formulated like this. From the set of input-output data, yi, ui, where I goes from 0, 1, 2 until n, we need to estimate the model order n and the system matrices A, B, K, and C. Over here, I will sketch a graph that will illustrate the system identification problem. This block represents the physical system. To this system, we can apply the control inputs and we can observe the outputs. When designing the system identification experiment, we often have a freedom to choose the control input. Control inputs are often chosen as sufficiently random signals, and over here I will illustrate such a control input. For example, we can select control inputs as pseudo-random binary signals or as filtered white noise. Over here I will sketch a filtered white noise. This is one sample, for example, at the time instant 1. This is another sample at the time instant 2. This is, for example, a third sample at the time instant 3. This can be, for example, a fourth sample, can be negative, etc. By applying this control input to our system, we will excite the system and we will observe the output. And over here, I will sketch the output. Again, on the x-axis, we put discrete time, and on the y-axis we will put yk. That is the outputs. If we apply such an input to the system, we will observe discrete time outputs. For example, we will observe something like this. And these are the samples: 1, 2, 3, 4. Perfect. During the system identification experiment, we record the set of input-output data that's represented over here. From this set of data, our goal is to estimate the state space model having this form: xk plus 1 is equal to a xk plus b uk plus k ek, and the output equation is yk is equal to c xk plus ek. But what do we mean when we say that we want to estimate the state space model? We actually mean the two things. First of all, we need to estimate the model order n. That is, we need to estimate the dimensions of our state vector. And this dimension influences the dimension of A, B, and C matrices. Secondly, we actually need to estimate the system matrices A, B, K, and C. But before we explain the subspace identification method, we need to introduce a test model. In our case, the test model consists of two masses, M1 and M2, that are connected by springs and dampers. Mass spring damper systems are used as models of a number of physical systems. For example, a car suspension system can effectively be modeled by a mass spring damper system. Also, electrical circuits can be modeled by using mass spring damper systems. Here is the sketch of the system once more. We assume that there is a force F acting on the mass M2, and this force F is our control force. That is, this is the control input to our system. First, we introduce the coordinates S1 and S2. S1 and S2 are the displacements of the masses M1 and M2 from their equilibrium points. To construct the system's model, we first need to construct free body diagrams. Here are the free body diagrams of the mass M1 and the mass M2. The force Fs1 is the force that the spring 1 is exerting on the mass M1. The force Fd1 is the force that this damper is exerting on the mass M1. Similarly, the force Fs21 is the force that the second spring is exerting on the first mass. Also, Fd21 is the force that this damper is exerting on the mass M1. And in the same manner, we define the forces Fs22, Fd22. We assume that the following model parameters are given: K1, K2, D1, D2, as well as the masses M1 and M2. K1 and K2 are the spring constants. D1 and D2 are damping constants. Next, starting from these two free body diagrams, and by applying Newton's second law, we obtain these two equations. Over here, S1 2 dots is the second derivative of S1. That is, S1 2 dots is the acceleration of mass M1. Similarly, S2 2 dots is the acceleration of the mass M2. Next, we introduce the state space variable. S1 is equal to new state space variable x1, S1 dot is equal to x2, and S1 dot is the velocity of the first mass. Then S2 is equal to x3, and S2 dot, that is the velocity of the second mass, is equal to x4. By substituting the state space variable in these two equations, we finally obtain our state equation, given by the equation number 5. We group all the state space variables x1, x2, x3, and x4 in the state space vector x, we form the matrix AC that depends on the model parameters, and over here, as we mentioned previously, F will be the control force, that is, F is equal to U. And finally, here's our matrix BC. Next, we need to select the output equation. We assume that only the position of the first mass can be directly observed. Let's look at the graph. Over here, we assume that there is a distance sensor that can measure S1. Under that assumption, our output equation takes this form. And if you multiply this matrix C by the state vector x, you will actually obtain x1. This state space model is in the continuous time domain. However, to be used as a test case for system identification, we need to discretize this state space model. To discretize the state space model, we use the backward Euler method. This method approximates the state equation like this. Let us explain this equation in more details. We start from the continuous time state space model that looks like this. X dot is AC times X plus BC times U. The main idea of the backward Euler method is to approximate the first derivative x dot like this: xk minus xk minus 1 divided by h, where h is the discretization constant. That is, we go back in time. We do that for stability reasons. By substituting this equation, in this equation we actually obtain xk minus xk minus 1 divided by h is equal to AC xk plus BC uk minus 1. And over here I deliberately shifted my input one step in the past to make all the equations consistent. From this equation we can actually obtain that xk minus h AC xk is equal to xk minus 1 plus h multiplying BC multiplying uk minus 1. Then, from this equation we obtain the following: identity matrix minus h AC xk is equal to xk minus 1 plus h BC uk minus 1. And finally, from this equation we obtain xk is equal to I minus h AC inverse multiplying xk minus 1 plus I minus h AC inverse multiplying h multiplying BC and multiplying uk minus 1. And this equation can be compactly written like this, where this part is now matrix A, and this matrix over here is now B matrix. They are also defined over here and over here. Before I explain Python code, I need to mention the following. All code files developed and explained in this video tutorial will be posted on my GitHub page. A link to my GitHub page is given in the description below this video tutorial. On the other hand, the output equation remains unchanged. That is, yk is simply equal to cxk. In the sequel, we present Python code for discretizing the system and for computing the system response to the control input signals. Here's the Python code. First, we need to import the necessary libraries. We need NumPy and we need plotting tools. Also, from NumPy linear algebra, we import inverse, since we will be inverting matrices. Next, we define the system parameters. They are masses, spring constants, and damping constants. Here is the system model, just for reminder. Next, we need to define the continuous time system matrices. That is, we need to define this state space model. We have matrix AC, then matrix BC, and here's our matrix C. Next, to simulate the state space model, we need to define an initial condition for our discrete time system. We assume a simply initial condition of zeros. Next, we need to define the total time for simulating the model, or better to say, the number of discretization time steps. We assume 300. Next, we need to choose the sampling time, or the discretization constant. This is our h in the backward Euler method. In our case, it's 0.05. Then we need to define the input. Over here, I'm simply assuming an input equal to 5, and 5 is constant during the simulation. That is, I assume that I apply 5 newtons over here. Next, I need to define the discrete time state space model. That is, I need to define these matrices, A and B. And here's how I do that. First, I define an identity matrix. Then, here's my A matrix, here's the B matrix, and here's the C matrix. After we do that, it's very good practice to verify the stability of both continuous time and discrete time systems. So let's do that. First, let us clear our workspace and let's clear our screen. Okay, and let's execute everything until here. And let's look into the eigenvalues. First of all, here are the eigenvalues of the continuous time system. Here they are. We can see that the continuous time system is stable, or better to say asymptotically stable. However, this stability needs to be preserved in the discrete time system. To do that, we need to compute the eigenvalues of the discrete time system. Let's see. Here they are. You can verify that these eigenvalues are actually inside of the unit circle. This means that the discrete time state space model is asymptotically stable also. That is, the discretization preserves the stability. Here's the function for simulating the state space model. But before we actually simulate the state space model, let us explain the basic principle. We need to simulate this equation. xk is equal to a xk minus 1 plus b uk minus 1, and yk is simply cxk. How to simulate the state space model? It's super easy. We start from initial condition x0 that is actually given, and then we simply recursively propagate this equation. We have that x1 is simply a x0 plus bu0, where we assume that also u0 is known. Then we can compute x1. y0 is simply from this equation cx0. In this step we computed x1. To compute x2, we will simply propagate this equation once more. We will write x2 is ax1 plus bu1, and y1 will be cx1. So knowing x1 and knowing u1, we can simply compute x2, and we do recursively this process until we compute all the states. This is exactly what is happening inside of this function. This equation is implemented over here, and we simply iterate through time steps. In our case, I is actually equal to k. We store the results inside of these matrices xd and yd. Let us explain that. xd will store the state sequences. That is, the components, or better to say the columns of this matrix, will be x0, x1, until the final time step, let's say xn. Similarly, the matrix yd, this is actually xd, and this is yd, will store all the outputs element-wise, y0, y1, until yn. To use this function, we need to specify the system matrices A, B, and C. We need to specify the initial condition. We need to specify the input sequence, and we need to specify the time. And this function will return the state and output matrices. Let's see what's happening over here. Okay, let's see our state matrix. Here it is. And let's see our output. Let's visualize the output. Over here, I will plot the output, and the output is the position of the first mass. Here it is. This is a typical step response of a system that is not well damped. Perfect. We are able to simulate the system. Now we are ready to derive the subspace identification algorithm. However, to simplify the derivations and for brevity, we first need to introduce special notation. Let dk be an arbitrary d-dimensional vector where k denotes the discrete time instant. This notation over here denotes this vector. Basically, what do we do over here? We take d vector and we start from the time instant I, and we stack all the vectors d on top of each other for different time steps, and we end with d at the time instant j. For example, the notation d 1, 4 will denote this vector. We start with d1, then we have d2, then we have d3, and finally we have d4. This procedure is known as the lifting procedure. Using a similar procedure, we define a data matrix dij with a superscript L, and this matrix is defined like this. The best way to explain this matrix is to give an example. For example, d 1, 3, 3 is defined like this. We start with the vector d 1, 3, and then we continue. D, what do we see over here? 2, 4, then we have d 3, 5, and do we see another vector? Yes, we have another vector, and that vector is d 4, 6. Perfect. If we decompose this matrix further, we will obtain d1, d2, d3, then over here we will have d2, d3, d4, then over here we will have d3, d4, d5, over here we will have d4, d5, and d6. This matrix is a data matrix. It consists of time samples of the vector d. Next, this notation over here, as well as this notation, are used to select certain rows or columns of a matrix. And this is the classical MATLAB and Python notation for selecting certain rows and columns of a matrix. However, for completeness, let us illustrate this notation. Let this matrix X be given as, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, what is X 1 until 2, all the columns? Well, this matrix simply selects these two rows of the matrix. That is, we will obtain this matrix 1, 2, 3, 4, 5, and 6. How about this notation? X, all the rows, columns from 1 to 2. This is equal to, let's see what's happening over here. We need to select all the rows and columns 1 and 2, and we obtain 1, 4, 7, 2, 5, 8. Perfect. And finally, we can derive the subspace identification method. The first step of the subspace identification method is estimation of the Varks model or the system Markov parameters. The abbreviation VARX stands for Vector Auto-Regressive Exogenous. And those of you who are familiar with time series will immediately recognize this model structure. From the output equation of our state space model, we obtain this equation. That is, we can express the innovation vector as a difference between yk and c times xk. By substituting this expression in the state equation of our model, we obtain this equation. Then, we can simply rewrite this equation like this. And this equation will be compactly written like this, where A tilde is this matrix, B tilde is this matrix, and we introduce a new vector zk composed of inputs and outputs. For the development of the subspace identification algorithm, it's very important to introduce the parameter p, which is referred to as the past window. Starting from the time instant k minus p, and by performing recursive substitution in this equation, we can obtain, first of all, this equation. Then, if we shift the time index starting from this time index one step, then we obtain this equation. And if we substitute back this equation inside of this equation, we obtain something like this. And if we proceed one step further, we will obtain this equation, and by back substitution, we will obtain this equation. Following this procedure, we finally obtain this equation. This equation is very important. By multiplying this equation from left with c and by using the output equation, we obtain this equation, where this matrix is known as the Markov parameter matrix. And this matrix is very important for the development of the subspace identification algorithm. Let us stop here for a second and let's analyze this equation. What's the physical interpretation of this equation? Well, the physical interpretation is the following. We can express the output of the system and the time instant k simply as a linear combination of past inputs and outputs. Why is that? Because this vector over here depends on inputs and outputs, and this term depends on past inputs and outputs starting from the time instant k minus p until the time instant k minus 1. Then we have this stochastic vector, and we have the initial state at the time instant k minus p. Here, it's very important to keep in mind that the matrix A tilde is a stable matrix. Why is that? Well, let's analyze the definition of the matrix A tilde. K is a Kalman filter gain, and this matrix can be seen as a state matrix of a stable observer, and consequently, even A is unstable, A minus Kc will be stable under the proper choice of K. Of course, we cannot select K since we are estimating the model. However, we can introduce this assumption under the assumption that we are dealing with Kalman state space models. Due to this fact, if we select P sufficiently large, we can simply assume that A tilde P is approximately 0. You can verify this by yourself. So take a matrix A tilde that is stable and compute sufficiently large power of the matrix AP, and you will see that the entries of this matrix are very close to 0 for large values of P. By substituting this assumption in this equation over here, we finally obtain this equation. And this equation represents the Varks model. It simply states that the output of the system at the time instant k is a linear combination of past inputs and past outputs. The first step of the subspace identification algorithm is to estimate this matrix MP-1. That is, to estimate the Markov parameters of the Varks model. It's very easy to estimate this matrix. So how to do that? From this equation, we can simply obtain this equation by simply stacking the vectors yp plus 1 until yp plus l, and from the right hand side of this equation we will obtain this part and this part. This is known since we can measure the outputs and we can measure the past inputs and outputs, which implies that this part is also known. This part is not known. On the basis of this equation, we can form this least squares problem, where f is the Frobenius norm, to estimate the matrix MP minus 1. The solution is a simple pseudo-inverse of this matrix, of this data matrix, given over here, and that's it. It's simple as that. To compute the matrix of Markov parameters, what do? We form this data matrix, we form this data matrix, then we compute the pseudo-inverse and we multiply the result by this matrix, and here it is. This is our matrix of Markov parameters. In the second step of the subspace identification algorithm, we need to estimate the state sequence. But why do we need to estimate the state sequence? The main idea is that if we would know the state sequence x0, x1 until xn, then we would be able to estimate the system matrices A, B, C, and K relatively easy. Why is that? To see that, let's go back to original state space model. Here it is. Let us assume that we know xk plus 1 and xk. Since we know uk and this term over here is a random term that we can also pre-estimate, then we can actually form a simple least squares problem to estimate A, B, K, and C. Let's see how to estimate the state sequence. Let us write again the equations 17 and 20. They look like this. By substituting the equation 26 in the equation 25, we obtain this equation. This equation is simply saying that the state at the time instant k is a linear combination of past inputs and past outputs. Besides the past window p, another user-selected parameter is defined in the subspace identification algorithm. This parameter is called the future window and is usually denoted by f. The future window needs to satisfy this condition. That is, it should be less than or equal to p. For a selected value of the future window f, we define this matrix. And for those of you who are familiar with control theory, you will immediately see that this looks like an observability matrix. In fact, this is an extended observability matrix. By multiplying the equation 27, that is this equation, from left with this matrix, we obtain the equation 29. Our next goal is to simplify this equation. We can simplify this equation by using the equation number 26. That is, we can neglect all powers of A tilde for the power index greater than or equal to p. This means that all these terms can be neglected, and as the result we obtain this equation. Now, let us analyze this matrix. Obviously, its first block row is the matrix MP-1. That is, the first block row is actually equal to the matrix of Markov parameters. Its second block row is the matrix composed of a block 0, and in addition, we have the entries of the matrix MP-1. And all the other block rows of this matrix can be constructed on the basis of the pre-estimated matrix of Markov parameters, that is, on the basis of the matrix MP-1. And by substituting the entries of the matrix MP-1 in this matrix, that is, by substituting the estimates, we obtain this matrix. That is, we can estimate this matrix. Now, let's take this equation and let's iterate the index k starting from k is equal to p until k is equal to p plus l. And let's stack all the vectors next to each other. As the result, we will obtain this equation. Let us analyze this equation. And I will zoom it over here. We are interested in obtaining an estimate of this matrix. That is, we want to estimate the state sequence. The left-hand side of this equation is completely unknown. This is because we don't know the extended observability matrix. However, we perfectly know the right-hand side. I said perfectly, but that's not the precise adjective. In fact, we can estimate the right-hand side. Now, can we somehow, by only knowing the right-hand side, determine this matrix over here? That is, can we determine the state sequence? Now, here comes the magic of numerical linear algebra. Under some assumptions, from this equation, that is from the equation 32, it follows that we can obtain an estimate of this matrix. And we can do that by computing a row space of this right-hand side. The row space of a matrix can be computed by using the singular value decomposition. That is, we take the right-hand side and we compute the singular value decomposition. The singular value decomposition will give us U, sigma, and V matrices, where U and V are orthonormal matrices and the matrix sigma is the matrix of singular values. Over here, we need to have an estimate of the state order. I will explain later on in the video tutorial when I discuss the Python codes how to estimate the state order. Over here, just a brief comment. We can estimate the state order by analyzing the singular values of this matrix, and more about this later on in the video. Now, under the assumption that we have an estimate of the state order, we can use the matrices sigma and V to estimate the state sequence matrix. We simply take the first n rows and columns of the matrix sigma, we compute the square root, and we take the parts of the matrix V. Perfect. Once we have estimated the state sequence matrix, we can actually extract its columns to compute the states. And finally, in step number 3, we need to estimate the system matrices. Let us write the equation 14 once more over here for clarity. This is the starting equation. From this equation, we have, what do we do over here? We can start with k is equal to p, substitute over here, and continue for k is equal to p plus 1, etc. By doing that, we will obtain this equation, where the right-hand side from this equation follows from the right-hand side of this equation. The matrix S is known. This matrix is known since we can observe the past inputs and outputs and we estimated the state sequence. Also, the left-hand side of this equation is known since we estimated the state sequence. Our task is to compute this matrix Q composed of A tilde and B tilde. We can do that by forming a simple least squares problem shown over here. And again, the solution of this least squares problem is given by the equation number 40. What do? We form this data matrix S and we simply compute the pseudo-inverse and multiply the result by the left-hand side, and we obtain an estimate of the matrix Q from where we can extract A tilde and B tilde estimates. Similarly, from the output equation of our system, we can form a least squares problem and we can estimate the matrix C by simply computing the pseudo-inverse of this matrix that is composed of the estimated state sequence and multiplying the results by this data matrix. Once these matrices have been estimated, we can obtain the system matrices like this. A tilde is simply the corresponding blocks of the Q hat, B tilde the same, and K hat can be estimated like this. And finally, our A hat can be estimated from the estimate of A tilde and the estimate of K and C. And that's it. To repeat, the subspace identification algorithm consists of 3 steps. In the first step, we estimate the system Markov parameters. In the second step, we estimate the state sequence. And in the final third step, we estimate the system matrices. In the sequel, we explain how to implement the subspace identification method in Python. To repeat, all the codes developed and presented in this video tutorial are available on my GitHub page. A link to my GitHub page is given in the description below this video tutorial. The first step is to import the necessary libraries. We need the NumPy library, we need the plotting tools, and from NumPy linear algebra we import inverse. Then, I've wrote several functions that implement the subspace identification method. These functions are defined in this file. And later on, I will explain all of these functions. Next, we need to define the model. Here are the model parameters, and here are the system matrices AC, BC, and CC of our test case given over here. That is, the model parameters and the system matrices of our mass spring damper system. Next, we need to define a few parameters. We are considering a system that has one input and one output. Over here, I select the total number of time samples for system identification. Time is equal to 300 time samples. Here is my discretization constant, h, of my backward Euler method. And over here, I discretize the model. I check the eigenvalues of the continuous time and the discrete time system in order to verify that the test case is stable. Next, I define an input sequence and initial state for the identification. Over here, I'm assuming a random input signal. Here it is. Let's execute everything and let's see the input signal. Here it is. We can also plot it. And we should be very careful when plotting, because this thing will obviously not work. Since we need to look into the shape, we need to do something like this. Okay, and then we need to repeat plot. And here it is. This is the input used for system identification. That is, I apply such an input to my system. That is, to this force F. However, I actually need two data sets for system identification. That is, I need two input sequences. The first input sequence will be used for system identification, and another input sequence will be used for model validation. And I construct another input that is statistically independent from the first input. That is, I simply generate a random sequence. Next, I need to simulate my discrete time state space model for two inputs. That is, I need to obtain the output of the validation data set and the output of the identification data set. And consequently, I need to call twice function system simulate. Here it is. And here's my output. This output is used for validation, and this output is used for system identification. Let's plot these outputs and let's see what will happen. For example, the identification output should look like this. Let's see it. Here it is. Perfect. The first step of the subspace identification method is implemented in this function. And in that step, we actually estimate the Markov parameter matrix. That is, this matrix. This matrix is simply estimated by forming the data matrices given over here and over here, and by computing the pseudo-inverse of this data matrix and by multiplying the result by this matrix. However, to implement this step, we need to select the past value and some other parameters. So let's look into this function estimate Markov parameters. This function is actually given over here, and let's find it. It should be at the top of the code. Okay, here it is. So what's happening over here? We provide the inputs and output vectors, and then we simply form over here the data matrices, and you can see this step over here. This step is actually this equation. Again, you can see what's happening over here. We're computing the pseudo-inverse of the matrix Z. That is, the pseudo-inverse is given by this expression, and we multiply the result by this data matrix. To repeat, this function performs the following. We form data matrix, this one, which corresponds to this data matrix. Then we form this matrix that corresponds to this data matrix. Here we fill the columns and rows of these two matrices, and finally we compute the Markov parameter matrix as a simple pseudo-inverse. Simple as that. However, to use this function, we need to select the past value. In my case, I selected the past value of 10. However, you can change this code and you can see what happens once you change the past value. Once we estimated the system Markov parameter matrix, we need to estimate the system matrices, that is, to estimate the state and the system matrices. We do that by using this function. However, before we even do that, we need to select the model order. The model order can be selected by analyzing the singular value decomposition of the data matrix. However, to make this video tutorial as short as possible, I will later on just give a brief several comments about the selection of the model order. However, over here I'm assuming a model order of 3, and I want to see what's happening. Let's analyze this function, estimate model. The inputs are the inputs used for identification. This output used for system identification, the Markov matrix returned by this function, matrix Z returned by this function, past value over here, and model order. Now, over here, I also need to select the future value. I select the future value to be equal to the past value. Let's go back to the post, that is to the tutorial, and let's see where the future value appears. The future value appears over here. That is when we form this matrix QP minus 1, and the future value should be less than or equal to P. Now, let us see the function estimate model. Here it is. Again, the inputs are input used for identification, the output used for identification, Markov matrix, data returned by the previous function, past and future windows, and the order estimate. So what's happening over here? Well, we simply form the matrix Q. Here's the matrix Q, P minus 1. And it's very easy to form this matrix. We can simply write one for loop to do that, and then we proceed. Then we need to estimate the state sequence. We compute the singular value decomposition, and finally we compute the estimated state sequence matrix. This matrix actually corresponds to the matrix given over here. And you can see how this matrix multiplication is implemented over here. And over here, of course, you can see that we are using singular value decomposition. Next, from the code line 122 until the code line 140, we actually estimate the system matrices. That is, we implement step number 3. We form these data matrices given over here. We form the least squares problem, and we compute the solution. We do the same thing for the matrix C, and finally we extract the matrices A tilde, B hat, K hat, and A hat, and we do it over here. Next, let's estimate the model by calling these two functions. I will execute everything from beginning. Okay, now we estimated the system model. Next, let's analyze the result. First, I will plot the singular values of this matrix sigma that's used for computing the state sequence. This plot is maybe the most important plot in system identification. Let's see this matrix. So here are the singular values of our matrix sigma given over here. What can we observe? We can see a huge drop in singular values, and we can see this drop after 4. So 0, 1, 2, 3, since Python starts indexing variables from 0, this corresponds to 1, 2, 3, 4. So after 4th singular value, we see a huge drop. This implies that actually the model order of the system is equal to 4. However, over here I assume the model order of 3. I did that since I need to start with a certain model order. So you start with some estimate of model order, you compute the matrix of singular values, and the matrix of singular values will actually give you a correct estimate of the state order. So here the correct state order is 4. And we know that because, let's go back to our model and let's ask ourselves the following question. What is the model order of this system? Obviously, the model order is equal to 4, and you can see the power of system identification and subspace identification method. You can actually see the correct model order completely from data. That's why I like subspace identification method. Next, we need to validate the quality of our model. For that purpose, we will be using the estimated system matrices and another data set. We will be using the validation data set. That is, we will be using the input and output of the validation data set. And note over here the difference. For identification, we used input identification and output identification. That is, we used completely different data sets from the data set that we'll be using for validation. That is, during the validation process, you use a data set that you didn't use during the system identification. The first step is to estimate the initial state. We are estimating the initial state by calling the function that we defined over here. We simply form a least squares problem and we estimate the initial state. More about this I will talk in my future video tutorial. I don't want to talk about initial state estimation since I don't want to make this video to be lasting for, let's say, 5 hours. So just use this function as it is. We estimate the initial state, and once we have that initial state, we can simply call this function system simulate. That's the function that I explained at the beginning of this video tutorial to compute the output and the state sequence that correspond to the validation data set. And then once we do that, we are actually simulating the validation data set, and we are comparing the outputs from the validation data set with the output obtained by simulating the estimated model. And let's compute the error. Over here, we'll see the error and we will see the variance accounted for that measures the quality of our model. Okay, we can see that the final model relative error is 42% and the variance accounted for is 82%. The variance accounted for of 100% means that the model is perfect. That is, it's perfectly estimated model. However, that rarely happens in practice due to the model nonlinearities, due to the process noise, and due to the measurement noise. This is first validation step, and you can see these two functions for computing the model error. They're given over here, and you can simply download the code and analyze these functions. Okay, another way of validating the model is actually plotting the output of the simulated model and comparing the output with the validation data set. And let's see what's happening. Here's the graph. The black line is the real output. That's the output from the validation data set. And the prediction is actually our predicted output on the basis of the estimated model. We can see that, okay, the model is kind of able to get the period of oscillations correctly. However, there is still some space for improvement. So let's improve these results. How can we improve these results? Let's try to, for example, to reduce the model order. This will not lead us to correct results, but however, let's see what happens. And let's see the results. So if we decrease the model order, we even get a little bit better results, which is not surprising, to be honest, Since there might be several dominating modes in this system, and the subspace identification method is actually performing model order reduction. However, let's assume the correct model order, for example 4, and we can see that from the singular values plot. And let's see what's happening. We can see a perfect match. We can see the final model relative error that's almost 0 and variance accounted for of 100%. This is a proof of principle that the implemented algorithm actually works. Okay, I can talk more about subspace identification methods, and I can make this video to be 10 hours long. However, I'm trying to keep this video tutorial as short as possible, and consequently I will stop here. You have all the codes on my GitHub page, and a link to GitHub page is given in the description below this video tutorial. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thanks a lot and have a nice day.